Starting today, starting to talk about spheres. We've pretty much covered every other shape. We've done pyramids, prisms, cylinders, uh, all those. We've done lateral area, surface area, volume. Today we're going to do the surface area and volume of spheres, the only thing we have left. Let's go ahead. Let's talk a little bit about vocabulary when you're dealing with a sphere. The radius of a sphere is the same thing pretty much as the radius of a circle. The distance from the center of that sphere to the outside and any distance to the outside. A chord, the chord of a sphere is the same thing as the chord of a circle. The diameter of a sphere, the distance all the way across that does have to pass through the center of that sphere. And then a tangent. We all know what a tangent line is. If a line skims and just barely touches that sphere at one spot, that line would be a tangent line. We know you could go a step further, a secant line. A secant line would cut through two different points. Surface area of a sphere. Next thing you need to write down. Surface area is equal to 4 pi r squared. First off, as you write that down, pi r squared. What is pi r squared? Area of a circle. Good. Here's how I want you to picture this. Anybody ever took a baseball cover off? Yeah. You know what it looks like, right? You've got, imagine this being a baseball's a sphere, right? You take the cover off of a baseball, it looks kind of like that. Right? And then you've got another one going the other direction. You've got two of those. Do you see what that is? Pretty much. It's two circles. And actually comes out as far as area-wise, it's exactly two circles. And then you've got another one going the other direction that kind of stitches to it, so you've got a total of 4 circles. So the surface area of a sphere, that's how you remember it. That's how I remember that formula. Is if you took a cover off a baseball, because surface area is coverage. How much does it take to cover that sphere? You could take exactly, that's what's pretty cool. This circle right here, this circle in the middle, called the great circle, you could take exactly 4 of those, and that's how much fabric, that's how much tile, that's how much whatever you want to think about. Whatever it takes to cover this, exactly 4 of those would cover that entire sphere. So 4 pi r squareds. There we go. First problem. Find the surface area of the sphere. Surface area is equal to, again, 4 pi r squared. The radius of this sphere. Dylan B, what is the radius of that sphere? 6. Good. So you got 4 times pi times 36. 6 squared. Which exact answer, 4 times 36 is exactly 144 pi. That's your exact answer. Leave the pi in there. Or if you type in 3.14 for pi, that's approximately 452.16. Now let's talk about units. This is surface area. Area is measured, that's coverage. Area is measured in centimeters squared. 144 pi or 452.16 centimeters squared. Next problem. Let's do the second one. Find the surface area of the second sphere. Again, surface area is equal to 4 pi r squared. Now what about lateral area? Lateral area, going back, reminder, lateral area is the area of all the sides of a shape. What about the lateral area of a sphere? Same thing. Lateral area, surface area, you have no bases. There's not a base there. So lateral area, surface area, it's the same thing. 4 pi r squared, the radius, in this case, Colton, is what? Yep. Good. So 4 times pi times 11 squared. Diameter is 22, 11, it'd be the radius. So you've got 4 times pi times 121. We can multiply that by 4. That's 484 pi. That's your exact answer, which is approximately, somebody got it?
1,500.
You're right. And that's in feet squared. Any questions? A few more vocabularies here. It says a plane, not an airplane, a mathematical plane. Not there's your plane. A plane can intersect a sphere in a point or in a circle. If you pass a plane through a sphere, you'll always get either a point or a circle. If the circle contains the center of the sphere, as it does over here, notice that circle, this plane is passing through the center. The intersection is called a great circle. The reason I call it the great circle is because that is the biggest circle that you could intersect through that sphere. Okay, if you intersected it down here, do you see how much smaller it is? If you intersected up here, you see how much smaller it is? But if you pass through that middle, that is the largest circle that can be intersected by that plane. So we call it a great circle. The endpoints of a diameter of a great circle are called the poles. North pole, south pole, right? Same thing, because if you take the Earth and you intersect a plane through the center of the Earth, well, this would be the south pole, this would be the north pole, right? The intersection, the endpoints of the diameter of a great circle are called the poles. Since a great circle, which it's got more than 2 poles, okay, everybody knows that, right? Since a great circle has the same center as the sphere, and its radii, that's plural radius, are also radii of the sphere, it is the largest circle, that's what I just said, it's the largest circle that can be drawn on a sphere. A great circle separates a sphere into 2 congruent halves called hemispheres. We know about the northern hemisphere, southern hemisphere. If you pass a plane through the equator, then you've got 2 hemispheres. Find the surface area of the hemisphere. And everybody's thinking, well, that's just easy. You just cut the surface area in half, right? Not exactly. Let's try that. How do you find the surface area? Let's find, what if this was a circle? Let's work it like that. The surface area of a sphere, if it was a whole sphere, excuse me, is 4 pi r squared, which would be 4 times pi times 2.8 squared. Here, I'll pull this up. We'll work it together. We leave the pi in there, so our answer is exact. So I'm going to do 4 times 2.8 squared. And I get 31.36 pi. And a lot of people say, well, since that's a hemisphere, you just cut that in half. So you would get the surface area. I'm going to do the surface area of the hemisphere would equal, somebody chop that in half for me, 15.68 pi. Anybody see a problem with that, though? Is that your total surface area? What happened when you chopped it in half? It now has a bottom. You see that? So if you want the total surface area, you don't just find the surface area of this hemisphere, just the top part, but you've also got the circle and bottom there. You've also got to find the area of that circle. So we're going to tack on plus another pi r squared, which I know we could have done that all in one step. So let's tack on 2.8 squared. So 7.84 pi. So we now have 15.68 pi plus 7.84 pi, which gives you a total exact answer-wise. Somebody type that in for me, please. 23 point. So 23.52 pi. That's exact answer. Approximate. 73.89, and that's in centimeters squared. Sometimes, though, it's easier to come up with a formula. Let's talk about how you would find the surface area of the hemisphere. See if there's an easier way. Anybody think of an easier way? Okay, surface area of the whole thing is 4 pi r squared, right? So the hemisphere, just the side part of the hemisphere would be how many pi r squared? 2 pi r squared. What's the bottom's area? Pi r squared as well. So the area of the sides is 2 pi r squared. The area of the bottom is pi r squared. So what would be the easiest way to do this? 3 pi r squareds. If you've got a hemisphere, you don't have to write that down. Just think about it. Just know it. If you've got a hemisphere, well, 2 pi r squared is going to give you the area of the side. 1 pi r squared is going to give me the area of the bottom. So to find that surface area, 3 pi r squared probably be the easiest way. Find the surface area of a sphere if the circumference of the great circle. I like these. It doesn't give you a radius. It doesn't give you a diameter. It doesn't give you any of that. It gives you a circumference. It says you've got a great circle there, and the circumference of that circle is 5 pi. So in essence, yeah, they do give you a diameter. 5. To find the circumference, if you don't remember, it's in your notes. The circumference of a circle is equal to pi times diameter. If 5 pi is the circumference, that's pi times diameter. Right there's the diameter, 5. So pretty much what they told you here is d is 5, diameter is 5. Now let's try to work it. Well, ignore that. So if the diameter is 5, surface area is equal to 4 pi r squared. Let's go ahead and go to our approximate answer. Anytime I ask you for approximate, it's easy, right? You just type in 4 times pi times, you just type the whole thing in, 2.5 squared. Straight to the answer, 78.5 meters squared. Any questions? Find the surface area of a sphere if the area of the great circle is approximately 130 square inches. How do you find the area of a circle? Let's see. Trace, you know how to find the area of a circle? Good. So area is pi r squared, and they gave us an area. And what we're going to do is we're going to use this 130. And notice it's already approximate. Our answer is not going to be exact. There's no way it can be exact because they gave us an approximate area. We're going to use that area to try to find a radius. If the area is 130, that means that pi r squared was 130. To find out what the radius is, well, first step, let's move pi over. Since it's being multiplied, let's divide. Go. And then to find out what the radius is, we're going to have to get rid of the squared. How do you get rid of the square? Square root. So there's your radius. The square root of 130 over pi. You'll type that in yet. So the radius is about, and that's approximate, right? We might as well leave it as that. The radius is about 6.43. So now it says find the surface area. Man, there's a whole lot easier way of doing this. Okay, now let's do that. Let's go ahead. We found our radius. I know the surface area is equal to 4 pi r squared, which would be 4 times pi times the radius, which we just found, 6.43 squared. Y'all be thinking about the easier way to work this. So here we go. 4. We'll go straight to an answer. 4 pi times 6.43 squared. So we get about 519.55. We call it 519.6. And again, that is rounded square inches. Now somebody will share with me the easy way to work that. How do you find the area of a circle? Pi r squared. How do you find the surface area of a sphere?
Oh, you just multiply that by 4.
Yeah. Pi r squared is the area of a circle. So this area, right, was pi r squared. This 130 is pi r squared. Well, to find the surface area, do you not do 4 times pi r squared? So could you not have just multiplied that by 4 and got 520, which that's a rounded answer? You sure could. Now let's move on volume of the sphere. Here's your next formula and last formula. The volume of a sphere, sorry I have no special way of remembering this. The volume of a sphere is equal to 4/3 pi r cubed, not pi r squared. Volume equals 4/3 pi times radius to the third. 4/3 pi r cubed. So, if you've got a circle, sphere, got a ball, three-dimensional. Let's say that you have a radius of 2 inches. I'll show you how I plug it in. I'll show you how you can No, you can plug it straight to the calculator. No problem. Radius is 2, so you got volume is equal to 4/3 pi times the 2 to the 3rd power. There's plugging straight into your formula. Which would be 4/3 order of operations. You have to do 2 to the 3rd first. That's 8. If you want it exact, put your 8 over 1. 4 times 8 is 32. 1 times 3 is 3. 32/3 pi. That won't reduce. Here's another way of working. If you want, well, if you're using a basic calculator, here's my thought. Here's what I normally do. I'll do my 3.14 times my 8 to find 1/3 of it. 8 pi. To find 1/3 of 8 pi, how do you find 1/3 of something? Yeah. When you're doing 4/3 of something, here's what I do. First step is I find 1/3 of it. To find 1/3 of something, you simply divide it by 3. 1/3 of 8 is 8 divided by 3. 1/3 of 9 is 9 divided by 3. 1/3 of 12, what is 1/3 of 12? 4. Okay, to find 1/3 of something, divide it by 3. Well, how do you find 4/3 of something? That's 4 of those, yeah. Divide it by 3 and then multiply by 4. If you're using a basic calculator, most of the time, that's how I do 4/3. Is I'll divide something by 3 and then turn around and multiply by 4. But now, if you're using one of these, you can type this whole thing in. You're going to go 4/3 in parentheses, 4 divided by 3, just to be safe. 4/3 pi times 8. So about 33.5. And that's in, since this is volume, we're filling, that's in inches cubed. Right here. 4/3, I do 4/3 in parentheses, pi, then times 2 to the 3rd power would be 8. Next one, we're finding the volume of a hemisphere. Now you could, if you wanted to, volume is equal to 4/3 power cubed. What if you only have half of a sphere over here? How could you change that formula? You can split it in half. How do you split it in half 4/3 power cubed? Could I do, well, split 4/3 in half. 2/3 power cubed. If you wanted to, plug it into that formula. Manipulate the formula. If 4/3 power cubed gives you the whole volume, 2/3 power cubed will give you half the volume. So that's one way of doing it. I'm just going to find the volume of the entire thing and just half it. That's how I'm going to work it. So here we go. 4/3 power cubed. So that'd be 4/3 times pi times the radius, which is 6 to the 3rd power, which is 4/3 times pi times, I believe that's 216. So if we want exact, again, you can take 1/3 of that. You can do this one in your head. 1/3 of 216, even without a calculator. Look, 21 and 6. Y'all recognize that those are both divisible by 3? What's the third of 216? 72. 21 divided by 3, 6 divided by 3. So you've got 1/3 of 216 is 72, but I need 4 of those, which I would believe would be 288. Take that 72 and multiply it by 4. So 288 pi. That's the whole volume. We're not finding the whole volume, we're finding half of a volume. So I believe that would be, instead of 288, that'd be 144 pi's. That's your exact half volume. And if you wanted that in decimal form and approximate form, that's about, I got it, 400. Point what?
38.
So 452.38 meters cubed. We're talking about volume again. We're filling it. You fill it with cubes. I don't know if it was this group or the second group I was telling you yesterday. If you're filling something, if you try to fill something up with squares, guess what? You'd never fill it. I don't know if you understand this. A square is two-dimensional. How thick is it? It doesn't have a thickness. If I drew a square on this board, that square has absolutely no thickness. Okay? It's not as thick as the board, it's not as thick as anything. It is flat, it is perfectly flat. So if you're trying to fill something, you can't use squares. You will never fill anything with squares because it has absolutely no thickness. You have to fill things with cubes. So when you're talking about volume, when you're talking about how much it takes to fill something, you're filling it with cubic meters, not square meters. Not meter square, but cubic. Here you go, the second one. A sphere with a great circle circumference of 8 pi, or 18 pi, excuse me. Well, that's pretty easy. If the circumference is 18 pi, well, circumference is pi times diameter. What's the diameter? Pi times 18, so the diameter is 18. So what I can just do, D equals 18, or R equals 9. We're actually going to need R instead of D. So we're finding the volume. Volume is equal to 4/3 pi R cubed. 4/3 times pi times 9 to the third. Here's another trick. Y'all ready for this one? It's all about math tricks this morning. 4/3 times pi times 9 times 9 times 9. That's what you're multiplying by, right? Can you cancel before you multiply? Sure. Make that a 1, make that a 3. So what you can do is just do 4 times 3 times 9 times 9. That's 12 times 81, which is what? So final answer there, 972 pi. Or if we wanted the approximate, 972 pi, which is about 3053.6. And that's in centimeters cubed, fill it with cubes. So there we go. Circles versus spheres. Make sure you know all these formulas. Circumference is 2 pi r, which I sometimes like pi d better. To find the circumference of a circle, you're either going 2 pi r or pi d. To find the area of a circle is pi r squared. To find the surface area, that's 4 circles. Because think about a baseball cover. And to find the volume, that's 4/3 pi r cubed. Make sure that you have all 4 of those formulas in your notes. It says the gemstones at the right are cut in exactly the same shape, but their sizes are different. And we've already talked about this, but these are 3-dimensional. They're still similar. Okay, they're still the same version scaled down of each other. And that's what we're going to do next. Identify congruent or similar solids. Similar solids have exactly the same shape, but not necessarily the same size. All spheres, think about that. All spheres and all cubes are similar. Take any ball, no matter how big it is, scale it down, they're similar. Okay, they're still a ball. Take any cube, whether it be the size of a house or the size of a dice, it's scaled down. All the different sides are proportional to all the different sides of the figure. In similar solids, the corresponding linear measures. Let's talk about linear measures. I hope I kind of have already, but just in case I haven't, let's talk linear measure. If I measure the distance from here to here, can I use a tape measure or a ruler to do that? Yes. Right? I could take a tape measure, measure the distance here to here. Could I use a tape measure to measure the distance from here to here? Or a ruler? Yes. What about, could I bend possibly if it was bendable, could I bend a tape measure and find the perimeter of the bottom of that? Those are linear measurements. The length of a side, the perimeter. What about a radius? What if this was a circle? Could I measure the distance from here to the outside with a tape measure? Well, kind of. If it was a circle, yeah, you can measure that. All right. Those are all linear measurements. The top of this shape is a triangle. Could I find the area of that with a tape measure? Could I measure the area of that with a tape measure? Can I measure an area with a tape measure? No. No. Area is not a linear measurement. This first shape, could I find the volume of this shape? Could I find out exactly how much it's going to take to fill with that with a tape measure? No, I'd have to calculate it, right? Linear measurements are measurements that you can find with a ruler or a tape measure, just by simply measuring. And we talked about a little bit about scale factors between linear measurements and areas before. Now we're going to do the same thing with volumes. But in similar solids, their corresponding linear measurements, which is their perimeters, their side lengths, their radii, if it's a circle, things such as height, radius, have equal ratios. Okay, they're proportional. The common ratio is called a scale factor. Been there, done that. If two similar solids are polyhedrons, their corresponding faces are also similar, but they won't have the same scale factor. We've already talked about that before. Two solids are similar if they have the same shape and their corresponding linear measurements are equal. That's what we've done. The ratio of this to this, the radius to the radius, will equal the ratio of the height to height. Or we could do this. The easiest way I find is to find that scale factor. What could I multiply R1 by? What scale factor could I multiply the first radius by to give me the second radius? You could take that first height, multiply that by the exact same S, and get that second height. I feel like that's the best way to do it. Congruent solids. Now, if it's congruent, they have the same ratio, but that ratio is going to equal 1. If two shapes are congruent, they're going to have a scale factor of 1. The heights will be the same, the slant heights will be the same, the bases will have the same lengths, everything will have a scale factor of 1. So here we go. Determine whether each pair of solids are similar, congruent, or neither. Okay, those two pyramids. Let's start out with the easiest first. Matt, are they congruent? No, they're not the same, guys. Congruent means the same in every way. These two pyramids are not the same. Now watch how I check. I'm going to check similarity by doing this because I want you to get extra practice. 8 to 12. Those are linear measurements. We can do this. I need you to take your calculator. I'll call somebody in just a second. I need you to take your calculator and tell me what is the scale factor from 8 to 12. What can I multiply 8 by to give me 12? Don't call it out. Now, as you're typing this in, I want you to realize you better get something bigger than 1. Because 8 times 1 is 8. 8 times 2 is 16. Actually, you need to get something between 1 and 2. 8 times a half is 4. You're going smaller. If you multiply by something smaller than 1, you're getting smaller. So something between 1 and 2, Jack, did you get it? 1.5. Your scale factor from this left shape to this right shape is 1.5. So now let's see, are these two shapes similar? If they're similar, that scale factor holds for every piece. I want you to take Dylan C. Take this 4. Multiply it by that same scale factor, 1.5. What do you get when you do 4 times 1.5? 6. So does the scale factor hold? Sure. So are those two shapes similar? Yes, they are. The second one, let's check it again. You have two rectangular prisms. I want to know, are these similar? Okay, first thing we're going to do, and if you like working the opposite direction, that's fine. If you want to go from the small shape to the large shape, that's okay. You can go either direction. Now we need to know what corresponds. First off, what does the 2.5 here correspond with over here? Be careful. 2.5 actually corresponds with 1.5. What does the 3 correspond with? And 6.2 with 3.4. And a lot of people are saying, how do you know that? The smallest with the smallest, the largest with the largest. Okay? So we need a scale factor. I need to know which way. Let's go this direction. 2.5 to 1.5. I need to know what can I multiply 2.5 by to give me 1.5. And for those of you that don't know how we're doing this, I'm taking 2.5. I'm multiplying it times some number, and I'm going to get 1.5. So to find out what that number is, you're simply doing 1.5 divided by 2.5. To get rid of division or multiplication, you divide. 1.5 divided by 2.5, I think you get 0.6. How do I know that? You want ready for another trick? Since we're all about math tricks today. Take this fraction. Take this fraction, and first off, let's do this. Let's multiply top and bottom by 10. 15 over 25. Multiply top and bottom now by 4. Or let's see, let's go the other direction. Yeah, we can do that. We'll multiply by 4. It gives me 60 over 100. 60 hundredths. You know how easy that is to turn into a decimal? 60 hundredths. If you can get a 10 or a 100 on bottom, then you can amaze people by your ability to divide 1.5 divided by 2.5 in your head, but not really. So that's 0.6. So your scale factor from, because it's shrinking, 0.6 is going to shrink a shape. From 2.5 to 1.5, your scale factor is 0.6. Now we need to know, does that scale factor hold true for all of them? Riley, what's 3 times 0.6? 1.8. Are these two shapes similar? No. Let's go ahead while we're at it. That's going to be 0.5 something. Because if you think 3 times 6 is 18, you knew it wasn't going to give you 1.7. Go ahead and multiply 6.2 times 0.6 and see what you'll get. It's like 3.72.
Yeah, that's right.
Oops. 3.72, not 3.4, not 1.7. Those two shapes are not similar. Now, are they close? Yeah, extremely close. Do they look similar? Yeah, but they're not. That's enough of that. That first one, though, we'll talk about it. Yeah, they're the same. They're just, one of them's laying on its side, the other one's laying up. This one has a diameter of 6.2. This one has a diameter of 6.2. This one has a height of 6.8. If this one was sitting up, it would have a height of 6.8. Those two shapes are congruent. Okay. Second one, you would test the same way. Okay, here we go. Last thing, the properties of congruent and similar solids. The cubes at the right are similar. Why? Because all cubes are similar. And, well, I can show you real quick. Watch this. Somebody with their calculator, tell me, what do you multiply 3 by to give you 2? 0.6 repeating?
Yeah.
Okay, 0.6 repeating. Okay, since this is a cube, this side is 3 and this side is 2 as well. Does it have the same scale factor? It's the same numbers, right? This side is 3 and this side is 2. Does that have the same scale factor? It's the same numbers. Okay, so how would they not be similar since every measurement is the same? So yeah, all cubes are going to be similar. So your scale factors are all the same. Now, here we go. So it says the cubes at the right are similar solids with a scale factor of 3 to 2. 3 to 2. 3 here equals 2 there. The ratio of their surface areas. If we found their surface areas, the surface area of the first shape, you've got 9, 9, 9, 9. You've got 6 surfaces, each having an area of 9 would be 54. The second would be 24. If you reduce that, the surface areas have a ratio of 9 to 4. Okay, so our linear measurement. The ratio is 3 to 2. The areas had a ratio of 9 to 4. We did that last chapter. Now, let me remind you though. If you have two shapes, if you find their scale factor, the scale factor between their sides, the scale factor between the radii, the scale factors between the perimeters, that is a linear scale factor. The relationship between that scale factor and the area scale factor is squared. Remember that? 3 squared, 2 squared. So if your original scale factor is 3/2, your areas will have a scale factor of 9/4. Well, what about the volumes? The volumes will have a scale factor of 27 to 8. You'll see the relationship. 3 to 2, 9 to 4, 27 to 8. That's actually 3/2, not to the second power, but to the third power. Do you see the relationships there? Because what you're doing is, well, what about this? Let's do another one. If you've got two shapes, let's say it's 2 cubes again. Imagine that was a 3-dimensional cube. I just have, that's the bottom of it. What if this one is twice, or let's say 3 times as big? Your linear scale factor is 3. To go from here to here, to go from this side to this side, you're going to multiply by 3. How much bigger would the areas be? Well, it's 3 times as tall and it's 3 times as wide. Does everybody remember? What's the relationship between the areas? It's going to be how many times bigger? 9 times bigger. Now, what if it was a 3-dimensional shape? What would be the relationship between the volumes? It would be 27 times bigger. 3 is your original scale factor, 3 to the second is your area scale factor, 3 to the third is your volume scale factor. Let's do another one with fractions. What if your original scale factor, your linear scale factor is 4/5? What's going to be the scale factor between the two areas? Give me a second to think about it. Or actually, Alex, what do you think? If 4/5 is the linear scale factor, which makes it will shrink, right? Well, how much will your area shrink? Not by 4/5. Your area will shrink by a factor of 4/5 squared. Does everybody understand how I did 4/5 squared? 4/5 times 4/5. Your volume, go ahead, Alex, and finish with that one. Your volume will have a scale factor of 4/5 cubed. 4/5 times 4/5 times 4/5. Everybody follow how I'm doing that before I go on and actually start working problems. So my question is, and here's, we can cover every difficulty you're going to have on these problems right here. Because what if I gave you this? What if I tell you the scale factor between the volumes, and guys, this will be on ACT, it's there. The scale factor between the volumes is 64 to 125. How do you go back to the linear scale factor? We've never done that. Let's work an easy one first. Linear, area, volume. The scale factor between the volumes is 8. It's 8 times bigger. You got two shapes. The second shape has a volume that is 8 times bigger than the first shape. What about their sides? Does anybody know how to go from here back to linear? How would you do that? Cube root. Okay, it's called a cube root. You may have found a cube root before. 2 to the third power is 8. Well, how do you go from 8 back to 2? That would be the cube root of 8, which is what we're doing here. You ask yourself, what multiplies by itself, not twice, like square roots. What multiplies by itself 3 times to give us 8, and that would be 2. So what's the scale factor between the areas? 4. Everybody try this one. I'm going to write it down and see what you can get. I'll come around and check you. Because like I said, this is where people have issues. What if the scale factor between the volumes is 27? I want to know what is your linear scale factor and your area scale factor. What do you think, Briley? What's the linear scale factor? 3. And here's the reason, guys. 3 to the third power. If you multiply 3 times 3 times 3, you get 27. So to go from 27 back to 3, you're doing the cube root of 27. So, Briley, what's the area scale factor?
9.
3 times 3 times 3. 3 times 3 is 9. 3 times 9 is 27. Okay, last one, then we'll actually work with problems. Give you a tough one. What if your volume has a scale factor of 8 1/25? I want to know what's the linear scale factor and what is the scale factor of the areas. Answer this. If 8 1/25 is your volume scale factor, does anybody know what the linear would be? 2/5. And what he actually did there was just ask yourself, what multiplies give you 8? 2 times 2 times 2, right? What multiplies give you 125? 5 times 5 times 5. So if 2/5 is linear, then area would be 4 and 25. 4/25. So now we're ready. Now we're ready for some problems. That's what I just told you. 2 similar cones have radii. Now when we're talking about the radius, that is a linear measurement. So we got linear, we got area, and we got volume. Radii lies here. So 2 cones have similar radii, or 2 similar cones have radii of 10 and 15. What is the ratio of the surface areas? So 10 to 15, let's start there. So we're talking about a radius, and we're going from 10 to 15. What do we multiply 10 by to give you 15? Now, I tell you what, instead of doing it as decimals, let's do this. Here's my scale factor. 10 times some linear scale factor is going to give me 15. Divide by 10, leave it as a fraction. What do you get? Divide by 5, divide by 5. 3 over 2. That's your linear scale factor. If you multiply 10 times 3 halves, guess what? You get 15. So what's going to be the scale factor between the areas, the surface areas? If 3 halves is linear, then what's the ratio of the surface areas? 9 and 4. They don't ask us, but can somebody tell me what's going to be the ratio between the volumes? 27 to 8. So if you took 27 and 8 and you actually divided that out, that's 3 and 3/8. I think that's 3.375. This is 2 1/4. This is 1.5. And if you did 1.5 to the second power, 1.5 to the third power, so what that means is your volume is going to be a little over 3 times bigger. Your area is going to be a little over twice as big if you took the area of the base or something. And your linear measurement is 1.5 times as big. Next problem, 2 similar prisms have surface areas. Now, this one's a little bit different. They give you 2 areas. They give you 2 surface areas. Linear, area, volume. You're here now. You're in the area. 2 similar prisms have surface areas of 98 and 18. What is the ratio of the height of the large prism to the height of the small prism? So you're going from large to small. So you're looking for, what can I multiply 98 by? I'm going to call it 98 times 8 because this is the scale factor of your surface areas. So 98 times something gives me 18. Go ahead and divide that. Let's leave it as a fraction. Reduce, you get 9 and 49. That's convenient. You'll see why that's convenient. The ratio of your 2 areas is 9/49. What that means is I can take my large area, I can multiply by 9/49, and that gives me my small area. 98 times 9/49 would give you 18. You can check that out at will. So I need the ratio of my heights. Where does height fall? Linear, area, or volume? Linear. You can measure a height with a ruler. So I need to go from area back to linear. How in the world do I go back to linear? Good. Square root of 9? Square root of 49. If you'd have left that as 18 over 98, it wouldn't have been near as easy. But since you reduced it and got 9 to 49, a whole lot easier. Now, they didn't ask for it, but the ratio of the volumes would be 27 and 343, I think. Moving along. By the way, this is one of the hardest things that people, I don't know what it is, that people have so much trouble with this. It's not bad, is it? They give you 2 volumes. LAV. Linear, area, volume. They give you 2 volumes. Let's find them. These are similar. Anytime it's similar, you have a scale factor. We're going to start with our volume scale factor. We're going from, let's go from the large to the small. 270 pi times some scale factor, we'll call it V, is going to give you 640 pi. The first thing to do, guys, remember me talking about reducing equations? What do I mark out? Now, yeah, mark those pi's out. And to get rid of 270, let's divide by 270. I actually marked the zeros out, which is dividing by 10. 64 over 27, I don't think that reduces. I haven't even read the problem, but let's finish this up. 64 over 27 is the ratio of the volumes. Has anybody got the linear ratio yet? Four over 3, and just for kicks, 16 over 9. So folks, that's all 3 of my ratios. If I have in this, if I have a surface area, let's say that they give me the surface area of the first one, I want to find the surface area of the second one, I use this. If they give me, like they have here, the height of the second one, and they want me to give them the height of the first one, now that's a little bit of trouble. Because if I multiply this volume by 64 over 27, I get the second volume. If I multiply this height by 4/3, it gives me the height of the second. So how am I going to go from 10 back to 4/3, or 10 back to h? Because usually scale factors, you're multiplying by something. You're going to multiply to go from here to here. Well, how do I go from here back to here? You divide. So to go from h to 10, I'm going to multiply by 4/3. To go from 10 back to h, I'm going to take 10 and I'm going to divide by 4/3. Or am I actually multiplying by 3/4? So 10 times 3/4 gives me 30/4, or 15/2, or 7.5. That makes sense, what we did there. Something else you might have just noticed. It's getting deep. This gets very deep. If 4/3 is the scale factor from left to right, what's the scale factor from right to left? 3/4. It's always a reciprocal. If 64/27 is the ratio of this direction of the volumes, if you wanted to go back this way, then you multiply by 27/64, which is the same thing as dividing by 64/27. That's the reason it works out the same. I think we got one or two more. This is the last one. A regulation volleyball has a circumference. So we got volleyball. And we're talking circumference. Is circumference an L, an A, or a B? Circumference. L. Its circumference is not how much it takes to fill it. Circumference is not how much it takes to cover it, but it's the distance around it. It's a linear measurement. I could take a tape measure, I could wrap it around that ball, and I could find a circumference. So a regulation volleyball has a circumference of about 66 centimeters. The ratio of the surface area, well, that's nice, they give it to us. The ratio of the surface area, which falls right here, is about 1.6 to 1. That's your ratio. Or you can just, why not just call that 1.6? What is the circumference of the children's ball? So the ratio of the surface area of the children, let's draw both of them. Draw this one over here. Let's say that's the children's ball. So if you're going from the circumference, that's a linear measurement, the circumference of this to this, you're multiplying by 1.6. It's 1.6 times bigger. But we want to know, actually no, that's the areas, isn't it? I apologize. We'll draw the areas to the inside. We'll say that the area of this circle, the area of this circle has a ratio of 1.6, but we want to know what's our linear ratio. How do you go from area back to linear? Anybody know? How do you go from area to linear scale factors? Square root. To go from linear to area, you square and then you cube. But to go from volume back to there, you cube root. To go from area back to here, you square root. So somebody find the square root of 1.6 for me, please.
1.26.
1.26. Is that exact? Okay. Leave it on your calculator then. So that means if I want to find the linear measurement, I'm going to multiply not by 1.6, but I'm going to multiply by 1.26, or whatever rounded off version you have there. So it says the regulation volleyball, this one has a circumference of 66 centimeters, but I need to go back. So instead of multiplying by 1.26, I'm going to divide by that 1.26. So you're going to take your 66, divide it by whatever answer you have on your screen, and you get what? About 52.17 centimeters. And you can always do this. Always use common sense when working these problems. We knew that this children's ball, children's ball is what they call it, should be smaller. If you would have multiplied instead of dividing, you got the wrong answer because obviously it would have been larger. And the children's ball, since it has a smaller circumference, shouldn't be a larger number. So always use common sense when you're working these problems. We're done.